So welcome everybody to the second session of today's quantum algorithms workshop. I'm very pleased to welcome Aram Harrow to open this session. Aram, as you all know, is a professor at MIT and will be telling us about small quantum computers and large classical data set. Aram, please.
Great, thank you. Thanks for the invitation, and thanks everyone for attending. Or watching after the fact, or however this talk finds you. So I was thinking for a while about how a quantum computer could help with machine learning, and it's been bothering me that machine learning has made progress on classical computers by using larger data sets. And we're hoping that quantum computers will help with them, but accessing a large hard drive does not seem to be one of their strengths. And so this is going to be my one attempt at dealing with this problem. And just to put the data issue in context a little bit, when you look at the quantum algorithms literature and when people produce algorithms, there are actually many different forms of quantum algorithms that can be divided up by input model. So the standard model is the one that, if you hadn't really thought about it very much, you would assume this is the only model. The input is like on a Turing machine, just bits on a Turing machine on a tape, or in a more real-world device, this would be the input comes down on the hard drive or from the RAM, and the output could be a bit, could be a string. And these are problems like factoring is an example of this. Grover's algorithm, not directly, but if you try to do combinatorial optimization, like try to maximize the number of satisfying assignments for a 3-set instance, that would fit into this standard model. But there are many other quantum algorithms that are useful to talk about that do not fall into this model. So one example is the oracle model. Instead of giving us the string explicitly as a string of bits, maybe we have query access to the string, meaning there's a subroutine O called an oracle that I can execute quickly. And I give it input I, and it'll extract bit x sub I from the string. And so here, you could think of it as the string is really an implicit input, right? We never actually see the full truth table of the function, but we can query it at select points. And this leads to many important quantum speedups like Grover's algorithm, the welded trees, hidden subgroup problem. And then there are other models, and these two models are both exist classically and quantumly. And then there are other uniquely quantum models. So we could have quantum data. Maybe our string is encoded in the amplitudes of an input vector. So this is what happens for the quantum Fourier transform, for example, why it can do so much better than the regular Fourier transform. Or quantum state tomography, or the quantum linear system solver all take input in this form. And finally, we can combine the above two rows and have a quantum oracle where what you're given is a black box function, a black box unitary. And that is itself the input to your problem. All of these are useful, right? We all like making progress on all of these models. But at the end of the day, if we have something in rows 2, 3, or 4, we probably want to find a way to convert it to row 1 before we're going to use it. For example, when Shor came up with period finding in the oracle model, that itself did not yield a useful application until they figured out how to instantiate the oracle for it and come up with factoring. And so that is the type of thing I want to think about how we can do, take things from rows 2, 3, and 4 and turn it into row 1 so that we can use it for a practical problem. Okay, so let me be a little more concrete. Another thing that's always bothered me has been Grover's search, especially the original title for the paper was Quantum Mechanical Search, of a database. And it just really does not feel like that is the right way to think about it. Because what Grover's search says, if I can compute a function f, such that f of I is x sub I, where x is some string, I want to find a 1 in that string. So we get a nice square root speed up, and this has applications to many other unstructured or semi-structured search problems. But this uses an oracle, right? We don't get direct access. We don't actually get the truth table of the function written as an input. Instead, Grover applies to a subroutine that can compute the elements x sub I. And this is good as far as it goes, but it really does not apply to a database, right? If we have this is a picture of a data center, if you try to send it a query in superposition, say, I would like to query a superposition of bits 3 and 4,072,000,000. It will break that superposition, right? It will just return to you randomly one of those two one of those two values. And even if we could query in superposition, we probably wouldn't want to, because if we're going to put 1 million hard drives in the data center, we might have 250,000 CPUs. In general, the number of CPUs will probably scale with the size of the data. And so any kind of thing where we just want to interrogate every record with a simple query, we can probably parallelize that. And that's probably a more efficient way of doing things. And one answer to this is to build quantum RAM, which is a memory. Sometimes people say quantum RAM, but they should mean quantum ROM. But basically, it's a memory that you can query with a superposition in the index register, right? So you can have a superposition of different locations that are being queried. And it could be quantum RAM, where you're storing writable qubits, or quantum ROM, where it's just read-only classical bits. Either way, what's important is that the input register be something that can go in superposition. This would address some of the problems, but it brings problems of its own. For one thing, it's not part of the standard hardware model of quantum computing. And that standard hardware model is hard enough, right? It's not easy to build 53 qubits like Google did and have them interact and have the thing not fall apart. And so as a theorist, I feel somewhat obligated to meet the experimentalists halfway and say, look, I'll just tell you what you need to do in the standard model of quantum computing rather than proposing additional hardware. So how can we do that? Suppose we have an algorithm that requires an oracle, but the hardware we have at our disposal does not look like that. It just is a hard drive with the bits x1 through xn just written on it. What can we do? Well, if you really need to make an oracle from this, one thing you can do is you can just sequentially query it. So you have these registers I, and the second one starts, let's say, 0, and you do a series of conditional gates. You say if I is equal to 1, you add x1 to the second register. If I is equal to 2, you add x2, and so on. At the end of this thing, you will have extracted the bit x sub I. It works fine if it's more than a bit. If it's a larger register, it works just as well. And to do this, it's important to know what you need. The quantum computer is some piece of hardware, like some trapped ions or some superconducting qubits, or maybe some kind of integrated photonic chip. Whatever it is, it's going to be, the actual gates are going to come from some kind of signal generator. And that thing is going to be programmed by either some custom built chip or by an FPGA. That in turn is going to talk to a laptop, which in turn can read a big hard drive. And the way it works is the laptop reads the next record off the hard drive. 17, I is 17, it reads off X sub 17. It turns that into a sequence of gates. So this thing where you do a controlled operation, you can break that down into elementary pulses. That's pretty straightforward, right? Once you know the value X sub 17, it's pretty straightforward to do that, to turn that into elementary gates. And then it sends it down the chain to the actual quantum hardware. And so what's important is that the quantum hardware, there's no sense in which it needs to directly touch the hard drive, right? And there's also no sense in which the size of the quantum computer needs to reflect the size of the data. Of course, you do pay, you pay a lot, you pay in time, right? So the time here is order n. It's an enormous amount of time just to access one lousy record. And so, what does this mean for quantum algorithms? If you have an order n overhead, what's the point? Like this is going to wipe out, certainly Grover speedups can wipe out a lot of speedups. And so, I'm not the first one to have grappled with this problem, sort of arguably the central problem of quantum algorithm design, or one of them. So one, you could change your hardware model, which I'm reluctant to do, or I think that's a valid line of research, but not one I want to engage in right now. And second, you could do what Peter Shor did. You could say, well, let me just come up with a good function. Like, let me just come up with a clever function f. What Peter Shor did is he said, well, a function f that I'm going to come up with is modular exponentiation. Map I to a to the I mod n. And then this thing, I can definitely compute that efficiently. And if I then find the period of that will solve a problem of interest. And that's great. But of course, we cannot guarantee that we'll always be able to keep on finding these functions. And for a lot of data problems, like I just have a bunch of cat and dog images from the internet, there's no reason to believe such a function even exists. That's just, it's just not the way that our problems tend to come to us. It may apply well to number theory or sort of extremely structured problems like that, but not just sort of run-of-the-mill machine learning problems where you just get a lot of data and you want to make some sense of it. Okay, so what can we do? One approach is that we can find ways to reduce the size of the data set. And I'm going to do this for problems that are fairly practical, that are things like clustering, Bayesian inference, and saddle point optimization, things that are really kind of mainstream machine learning problems that where we really would welcome any speed up. So let me be a little bit more concrete about what I'm proposing. So the problems I want to consider are problems of statistics using data. So let's be very concrete. One such problem is maximum likelihood estimation, or perhaps you should call it maximum a posteriori estimation. The idea is you have a class of models Y and a data set X. And you want to find the best model, so you're maximizing over little y belongs to the set capital Y. And what does best mean? Well, there's some function R of Y that tells you how much you preferred the models in the first place, even in the absence of any data. Maybe some of them are simpler, or you're doing in the Bayesian setting, you could have a prior. And then you have a measure of how well each point fits a given model. So you can think of it generally as a loss function, or you can think of it as a log likelihood. It's the log of the probability of observing data point X given model Y. Okay. And if you add up these logs, then you get the log of the total probability of observing the entire data set given a given model, assuming that the data set is drawn independently from this distribution, P of X given Y. So just a very standard inverse problem in statistics. You get a lot of data, and you know how to go from a model to the data. That's just drawing samples. To go in the other direction, you want to find the most likely model. So what can you do with a quantum computer? And I'm going to focus on Grover because Grover is almost 25 years old, and I entered this project. I still didn't have a good sense of how to use it for these very basic problems. But in your mind, when you hear Grover, think optimization algorithm of your choice, right? So you could do adiabatic, quantum walks. If there's something smarter than Grover, you could use that instead. I'm going to focus on Grover just for concreteness, but it's not really essential to what follows. Okay, so assuming we're doing Grover, these sets X and Y appear almost symmetrically in this expression. Okay, so we're maximizing over Y and we're summing over X, but both of those are amenable to a Grover-style square root speedup with a few caveats. So that difference is not so essential from the perspective of quantum algorithms, but there's a bigger difference, which is the type of set, the type of data set that they are. So X is a data set. It lives on a hard drive, and we cannot query it in superposition. We do not have Oracle access to it. Whereas Y, you might call it a synthetic data set. It's like the output of the modular exponentiation function. It's something that is, it's implicitly defined. We never actually write out all the elements of Y. Instead, we have some algorithm that can spit out the different elements of Y on demand. If we ask for a particular one, we can just generate that. We don't have to consult any database. So, for example, if we're doing a clustering problem, Y might be the centers and the weights, the covariance matrices of the different clusters. So there we can make superposition queries. For X, we cannot. And so that difference leads to an asymmetry in our ability to apply Grover. If you go back to the model I mentioned, where you have a classical computer with access to the data that is also controlling the quantum computer, the number of evaluations of f you'll need will, for the outer loop, you'll be able to get it down to the square root of the size of y. So instead of just searching over all possible y's, you can get it down to the square root. But for the inner loop, you just have to pay the full price. You just have to still enumerate over the whole data set. There's no shortcut because we don't have superposition access to the data. And so then the natural question to address is, can we reduce the dependence on x? Can we, this x might be a dominant term in our scaling. Can we cut that down? And the approach I want to propose for that is one that's well known to the classical machine learning literature. It's called data reduction, or producing a coreset. The idea is, here's your data set X. Suppose you'd like to cluster it. Then from the perspective of clustering, you might be able to get away with something smaller. Not the original full data set, but just some weighted subset of the points. And in particular, what you'd like is that for every possible model that you consider, it evaluates something similar on X or on the weighted coreset X prime. And maybe I'm calling the coreset X prime, but I guess I could say X prime and the weight W. So let's be a little more concrete. So for all models Y, on the left we have the true log likelihood, the true score of your data set X. And on the right you have some approximation from the coreset where you only sum over the points in X prime and they're weighted according to some function W. And it's not hard to see why you should need some kind of weights, because the number of terms on the right-hand side is much less than the number of terms on the left-hand side. So you have to make up for that somehow. But it's also often important to have uneven weights, to weight some terms a lot more than others. And we'll see that the reason for that when we get to importance sampling. So yeah, anyone, please stop me if you have questions. I guess you can do that via the Slack, because yeah, so normally I would pause and look around the room for questions, but I don't see anyone in the room, so I'll keep going. But I welcome your questions on Slack or whatever the channel is. Okay, so good. So what can you do with these coresets? How does it all fit together? You have a data set X, you feed it to a classical computer, it crunches it down to a smaller X prime. This in turn gets fed to a quantum computer that tries to find the best model, and it outputs some model Y. Now let's, in a little bit more detail, how might you do this? Like how does the classical computer find X prime? What it can do is it can first try to solve the problem in a very approximate way. For clustering, for example, that's kind of the main example I'm thinking of here, although it's not essential to be clustering. For clustering, what you might do is something called a bi-criteria approximation, which means in clustering, you might be looking for the best clustering with, let's say, 8 cluster centers. Bi-criteria approximation is the one where you say, instead of 8, let me look for 80 cluster centers. And also, I'll tolerate a clustering where even with 80 cluster centers, it's not as good as the best one with 8. Right? So very crude, wasteful, both in the quality of the approximation and in terms of the number of centers. That's okay for what follows, because you're not using Y prime to directly give you the answer. You're just using it to construct importance sampling weights, which tells you basically the probability of including a given point in the coreset. Then using these weights, you draw X prime using importance sampling. Then on the quantum side, once you have this input X prime, paying that oracle price is no longer so bad. If X prime is a lot smaller than X, then we don't mind, we don't mind paying that order n cost. Sweeping through the entire data set no longer becomes a dominant part of our runtime. So the inner loop cost is the size of X prime. The total cost is the size of X prime times the square root of the size of Y, or replace this with whatever your quantum algorithm takes. You can see whatever the quantum algorithm is, there's always an inner loop where you evaluate the cost function, right? And this would improve upon that. This gives you, so for clustering, if you want to do exact clustering, the best classical algorithms are already of this form. The best known classical algorithms, I should say, not because there's always a better one. The best known classical algorithms are to construct a core set and then classically brute force over all clusterings of that core set. And the runtime is dominated by this brute force search. And so this is something that becomes very amenable to quantum speedup because most of the time is doing brute force search over a small data set. Even though you started with a lot of data, in the end, it boils down to something that's very amenable to a Grover type speedup. So let me give a little bit more detail because I think what I did was a little high level, a little bit more technical detail about what I mean by the importance sampling and what the criteria are. So remember, our goal is for all models Y, the true score of the model should be close to the one that you get from the core set. And here, this is a little bit stringent. You don't have to, technically, it doesn't have to be for all Y. It could just be for the best Y. That would also be. So it turns out it's not too much harder to do it for all Y, so I'll just consider that case. So to get that to work, what are your, what goals would you like? So you can think of this as X prime and W are like an estimator for the true log likelihood. And this estimator should have a few properties. It should be unbiased. So these two sides should be equal in expectation. Then, of course, once the expectations are equal, you'd like the variance to be not too large. And then that's only for a fixed Y. You want it to work simultaneously for all Y. So each of these gives you some constraints. For the first one, this tells you that the probability that you, let's say we choose X with some probability S of X, then the corresponding weight should be 1 over S of X. So in other words, we might choose points, we might bump up the probability of choosing some points, but if we do so, we should then put them into the sum with a lower weight to compensate for that. So the expected weight that we get from each point is always the same. So that'll make this top equation equal in expectation. Next, you want to choose points more often if they are very influential for some models. So the this right-hand quantity is the sensitivity of a model Y to a given point X. So let's look at this. This is looking at all possible models Y, and then for that model, the denominator is the total log likelihood or the total cost of that model. You could also think of it as the total loss. And the numerator is the one corresponding to point X. And so this is saying what fraction of the total score of a model can be attributed to a single point X, and then maximize it over all models. So this could be as large as 1, but often we hope it's a lot smaller. And it turns out that if you choose S to be at least as large as this, then that will give you a way of controlling the variance. Now, if you look at this quantity directly, it looks a little bit grim because we're maximizing over Y, and then inside we're summing over X. Because that looks like that's as bad as the original problem. But the important thing here, the thing that makes the whole project work, is that we just need an upper bound for it. We just need S to be an upper bound for this quantity. It can be a crude upper bound. And then that will, the worse that bound is, the bigger our core set will be. But as long as we choose our core set to be big enough corresponding to the values of S that we pick, that we never have to compute the right-hand side, because that would be too much to ask. And finally, if you want this thing to work for all possible values of Y, then you can do it by a union bound over Y, but maybe Y comes from an infinite set, or maybe that's wasteful anyway. So the way to do that is you can bound what's called the pseudo dimension of the family of models. If you know VC dimension, pseudo dimension is pretty similar. basically it's a model of how complex these models are. And let me just give you a little example to make all this more concrete. First, so what does this give you? So let S be the total sensitivity, the sum of all these S of X's. A priori, this could be as large as N, but we hope that it's much less. And then the size of the coreset that we need, M, scales like S squared over epsilon squared. Epsilon is the approximation error, and times the pseudo dimension D plus a term that depends on our willingness of having a small chance of failure. Now, if S is growing with N, this might be really bad. This might be even vacuous. But it turns out in many examples, S does not grow with N. It only grows with the complexity of the model that you're fitting, not with the size of the data. For example, k-means in D dimensions. So k-means means you have k cluster centers, and F is your scores, like minus the loss, which is basically the squared distance to the closest cluster center. Doesn't quite look like the log of a probability, but it's closely related to a mixture of Gaussian's model, which has a similar cost. So in that case, it turns out that the pseudo dimension and the sensitivity only depend on the dimension, D, and the number of cluster centers, K, not on the number of points, N. And so the size of your coreset will be independent of N. It will just depend on the complexity of the model and the quality of the approximation that you want. And so what the algorithm is the classical computer just needs to find S of X, so not the true sensitivity, but just its upper bound. And it can do that with a very crude bi-criteria approximation clustering, samples the coreset, and then the resulting brute force search is very amenable to a Grover type speedup. Okay, so this is one way of using a quantum computer with a big data set for a practical problem, and does not require any new data access rules. However, as a quantum algorithm designer, I find it in some ways unsatisfactory, because you could say, well, look, this problem, yes, it had a very large data set, but it turns out because of the class of models you were fitting, you didn't need all that data, right? It turns out it was reducible. And the interesting task of reducing the data, that fell to the classical computer. And so also the classical computer is the one that acquired the data. So, the role of the quantum computer here is somewhat minor. And it's, really maybe the problem was not as hard as you thought, rather than it being something you knew that the quantum computer could do. So is there a way of using the quantum computer in a more interesting way? Maybe one way is, again, there's a big data set, too big for the quantum computer to really access. But by doing some interactive computation, the quantum computer can effectively query that large data set. Of course, it cannot query superposition. The only way it can do it is with communication through the classical machine. So when can that be beneficial? And here, I'm going to describe to you two algorithms. One of them is quite general and is a heuristic. I don't have a provable performance guarantee, but I think it's promising. And the other one is something where I have provable bounds on its performance. So the problem I want to consider next is a close variant of maximum likelihood estimation, where the goal is not to pick the best model, but to sample from the posterior distribution over models. So let pi naught be our prior distribution over models. F of x comma y is again the log of the probability of observing x given y. Then Bayes' theorem says that the posterior distribution pi of y is given by this expression. And if we can sample from that, then we can not only figure out approximately what is the most likely model, but we can get things like uncertainty intervals around it. We can say, which events are we likely to see most of the time, things like that. Often it's more useful than just a point estimate. So how can we do that? So one algorithm is to say, suppose I've built up the coreset this far. I have points x1 through xt and corresponding weights that I send to the quantum computer, then the quantum computer can solve a sampling problem corresponding only to this limited set of information. So it's instead of sampling from the true posterior distribution, which you could get by having a the entire data set, you sample only from the distribution that you get from this core set. So instead, basically, you have this weighted sum of f's inside the exponent, basically corresponding with replacing the true data set with the core set. And in the tth round, it produces a sample y sub t, and then the classical computer needs to choose the next point of the core set using all the information it's seen so far. So using x1 through x sub t, using the weights that it's seen so far. So this is basically the existing core set, as well as all of the models returned by the quantum computer. So using all that information, the classical computer has to find another point for the core set. Okay, so this is fairly general. The references I gave above gives several different prescriptions. Maybe I'll briefly describe one such prescription. The idea is that, and just to remind you, a prescription for updating the core set, right? So what I've described to you is I've specified everything except for what is the classical computer actually doing when it adaptively adds points to the core set. So one way you can do this is you can say, let me work in the space of models. So cat y will correspond to model y. Then a data point x corresponds to this vector where I have a sum over all of the models with the coefficients given by f. And then in this picture, I can say the exact log likelihood is a vector, right, with an entry for every model, which is just given by the sum of all the data points. My core set approximation is, some other vector. And the residual is, of course, the direction I want to go in. So if I'm picking another point to add to the core set, what I want to do is go in the direction of that red arrow. So it's a very natural thing to do, a little bit like the Frank-Wolf optimization algorithm, if you've seen that before. You're going to choose the next point to maximize the inner product with the residual. And here it's convenient to normalize by S for reasons kind of similar to how we were using S before. And then once you have the data point, how you choose the weight, this is just a 1D optimization. You can choose that with line search. So this is all well and good, but if you look at what's going on, we have to maximize this, we have to look at the whole data set. And then this inner product involves searching over all models. So that's the size of all the models times the size of all the data sets, of all the data points. That together is as bad as just brute force search solving the problem in the first place. So to make this a little bit more efficient, we don't look over all of the models. We just say, well, let's look at the most likely models, and those are the ones that have been returned by the quantum computer. So if the quantum computer has returned samples y1 through y sub t, to estimate this inner product, we instead of summing over all models, we only sum over the samples that we've seen so far. And so the calculations take time. That's the size of the data set, which we were prepared to do anyway, times t, which is the number of rounds we've done so far. So if the number of rounds is not too big, this will not take too long. So, so this idea is not mine, by the way. This is due to Campbell and Broderick, but it's basically the classical piece of this algorithm. And we do not know a rigorous runtime guarantee for it. I mean, they have a guarantee, but it's in terms of parameters that in general we don't know. So I would just call this a heuristic algorithm. So the third algorithm I want to present is one that is where I can actually say something provable about how well it works. And this is to solve the problem of saddle point optimization. So let me say what I mean by that. It's going to be a slightly different definition of X and Y. So you still have a database, X1 through X sub n, and capital X will no longer be that set, it will be the convex hull of that set. meaning the smallest convex set that contains them. Here's a little picture of an example of a convex hull. And Y will be the probability distributions over M items. So you can think of them again as something that we have superposition access to, like M different models, except the difference is now we can output not just one model, but we can output some probabilistic mixture of models. And this happens a lot. For example, in boosting, something like this happens. And it makes sense also that maybe the computer would say, I don't know exactly which model it is, but I have, I think it's 30% likely to be this and 10% likely to be that. Or you could say that this, maybe your goal, the X1 through Xn are a bunch of customers that have demands and you need to meet all of those demands. The Y represents strategies that you're allocating resources towards. And the algorithm, by outputting a probability distribution in Y, basically is sort of fractionally dividing resources among these different strategies. So whatever it is, the mathematical problem we want to address, however it came about, we also want f of xy to be linear in x and y. So when I take a distribution over things in y, I want to think of f as as just basically giving me the average of f evaluated at each of those individual points. When you meet all these conditions, then you get von Neumann's Minimax theorem, that the maximum over y followed by the minimum over x of f of xy is the same as what you get by changing the order of the min and the max. And this is the thing that we want to compute in saddle point optimization, this minimax quantity. So this is a little abstract. What does it actually correspond to? So one thing it corresponds to are zero-sum games. If you, the Y player is trying to maximize things and the X player is trying to minimize things, then this is, that's one thing that corresponds to this expression. Of course, it's important here that to remember the data issues, right? So the X player should be looking at a classical database. The Y player should have a set that can be accessed in superposition. Another thing in this family is linear programming. So if we're trying to find a point in Y that meets all the criteria, satisfies all the linear constraints given by Y, then that also fits this family. We could say that f of xy is negative if the constraint is violated, and it's non-negative if the constraint is satisfied. And so you'd like to know, is this maximum greater than or equal to 0? If so, then you can satisfy all the constraints. If not, then you cannot. It also looks kind of like maximum likelihood estimation, right? For the only difference is we have a min over x instead of a sum over x. But if that sum were dominated by the lowest point, like let's say there's a clustering problem and the score of the clustering is going to be really dominated by the outliers, then it becomes a reasonable approximation for maximum likelihood estimation. And maybe that approximation is what you wanted in the first place. Maybe you just really care about the outliers more than about the average performance. If you're familiar with SVM, this looks a lot like a kernel SVM, but with the L1 norm instead of the L2 norm. And it's really basically like, how can you separate the points with a simple hyperplane, and where simple is defined with respect to the L1 norm. Okay, so let me describe to you the algorithm, and again, it borrows on an old classical algorithm, but one that that works well in the quantum domain. So the algorithm is due to Grigoriadis and Khachiyan from 25 years ago, and I'll describe it for the game of rock, paper, scissors. The algorithm is called fictitious play, and you just imagine the two players are playing against each other and trying to do a good job. But the important thing is that they don't try to just do the best response strategy, because that you can see pretty easily is not going to work. Like for rock, paper, scissors, one player does rock, the other does paper, the other does scissors, the other does rock. It's just going to cycle forever. Okay, so you have to do something a little bit different to make it converge, And what you can do is introduce a little bit of randomness. Turns out you can do it for just one player, but for simplicity, I'll do it for both. So let me illustrate how that works. The X player will choose X1 arbitrarily. Let's say that she chooses rock. And then this purple line is the induced payoff vector for the Y player. So here, the Y player is trying to maximize things. And so, paper gets a score of 1, scissors gets a score of -1, meaning that if Y does paper and X does rock, then Y wins, that 0 here is a tie, etc. So what the Y player will do is choose a response that is biased towards the better responses, meaning the higher numbers, but not always pick the highest one. And so the weighting will be this. It'll be e to the epsilon times the score will, once you normalize that, that will give you the probabilities of each response. So paper is the most likely, slightly, just a little bit more likely. Rock is in the middle, scissors is slightly less likely. So suppose that the Y player happens to choose paper. Then go in the other direction. This now induces a payoff vector for X. X does the same thing, except X is trying to minimize. So there's a minus sign on the exponent here. And suppose that X also chooses paper. So now what? Now, when we go back to the Y player responds to the sum of each of these rows. So we see that initially, all the probabilities are very close to equal. So these players are almost guessing randomly. But as you go on and you start adding up these rows more and more, the probability of a bad strategy starts to go down exponentially. And so this will converge fairly rapidly to something that is an approximate Nash equilibrium. And they can prove this. So if you want to have an error that is epsilon times the largest entry in the payoff matrix, the number of rounds goes like 1 over epsilon squared. So that dependence is not so good. But it seems like you can't do better for this class of algorithms. But it also scales logarithmically with the size of the strategy sets X and Y. And so this is, this is very good performance. You don't have to, you can see that you don't even have to look at all of the payoff pairs, right? Even on a classical computer, if this thing is n by n, this will be n log n over epsilon squared. The entire payoff matrix is n squared. And so you might never even look at all n squared entries, which is pretty remarkable that you can find an approximate Nash equilibrium and not even see some of the entries. And so how does this work on a hybrid classical quantum computer? So there's capital T rounds of alternation. In each round, the classical computer has to look at its entire data set. And the inner loop, what it does for each record, it has to look at all of the T strategies that the quantum computer has sent it so far. In the other direction, the quantum computer has to use Grover, or your optimization algorithm of choice, with order T calculations in its inner loop. Because for its inner loop, it has to look at the T strategies that the classical computer has sent over. And so if T is small, this is close to the best possible, because you are already doomed to look through the data set at least once and to do at least one Grover iteration with a very simple inner loop. And so what this is saying is you just increase that by a factor of T squared, right? T repetitions and then T things in the inner loop. And so if T is small, then this is close to the best that you ever could have hoped for. So those are the algorithms I want to propose for large data sets and small quantum computers. I want to comment briefly on how this connects to other hybrid quantum algorithms. When people talk about hybrid classical quantum algorithms, or they talk about NISQ quantum algorithms, what they usually mean are variational, right? So the goal is pretty much always you want to minimize some Hamiltonian, you have some ansatz that depends on some parameters T. For example, in QAOA, these A terms are either your objective function f or some of sigma x's, or in the VQE, then they might correspond to pieces of the Hamiltonian. And there's usually some classical outer loop such that the classical computer is searching over the T's, and the quantum computer is being used to evaluate the cost function. And this is one of the most common classes of practical quantum algorithms, although it's somewhat heuristic in that there are a lot of things we don't really know. So we know that it's exact as p goes to infinity, but what we really care about is if p, the number of steps, is small, like 4, 6, how good of a job does it do? And we really just don't know that. So one thing that I've worked on is to say, how does the 0th order versus a 1st order algorithm compare? So 0th order means that you're just evaluating the cost. 1st order means you're evaluating the gradient of the cost and feeding that to some different classical outer loop. Of course, you could also have 2nd order where you evaluate the 2nd derivatives. And let me just skip this slides. One thing that we found is for a very simple ansatz, very simple Hamiltonian, one where you just have uncoupled single qubit terms, we can show that 1st order beats 0th order. So in other words, that gradient measurements provably outperform direct energy measurements. And this was a bit of a surprise in some ways because some of the early work had said, don't use gradient measurements. Because if you use direct energy measurements, most of the terms of the Hamiltonian commute, right? The Hamiltonian can be divided up into maybe 2 or 3 blocks of non-commuting terms. You can measure all the terms in a block at once. Whereas if you measure the gradient, it turns out you can only measure one term at a time, and they don't usually commute. So you often lose a factor of n there. You don't in this case, but in many cases you do. But we can show is that the number of queries you need for 0th order is at least n cubed over epsilon squared. I mean, that's also achievable. And for 1st order, you can do an n squared over epsilon. So even if you lose a factor of n, you still come out ahead with gradient observables. So that was one thing that we worked on in this space. But what I want to talk about more are the connections between these variational algorithms that are well studied and these big data algorithms that I've been proposing. And one way to see the connection is to think of these as different ways of doing gradient descent. So conventional gradient descent, you could say what you're doing is you find the gradient and you take a little step in the direction of the gradient. Or I guess if you're in minus the gradient, if you're trying to go down. So, but there's another way of thinking about that, which is to say, I want to move in the direction of the gradient, and I want to balance my desire to move in the direction of the gradient with my desire to not move too far. Because, why do I not want to move too far? I want to be conservative, and I believe that the gradient is sort of a locally valid approximation, and I think that approximation is going to break down if I get too far away, right? And if I knew things about the eigenvalues of the Hessian, that might tell me how quickly it's going to break down. So that's what this first equation says. It says xt is my point. I'm going to choose xt plus 1 to minimize the sum of 2 terms. There's like a parameter eta that tells me the relative weight of those terms. The first term is my inner product with the gradient. So, I'm trying to move in negative the gradient direction. That's what this first term tells me. And the second term says, but I don't want to get too far away in 2 norm, in Euclidean distance. And you can do a little calculation. You can see that this will just recover for you conventional gradient descent, where you just move minus eta times the gradient is basically what this algorithm does. Maybe off by a factor of 2, but that's basically what it does. And when you formulate gradient descent this way, you say, okay, what's the point? This is the same as the original one. Then you realize there was nothing magical about the Euclidean norm. For some problems, that is the natural metric. For others, it might not be. For example, if you're working with probability distributions, you might prefer the relative entropy as a metric. And so that's what mirror descent does. I mean, mirror descent replaces it with the general metric, but one common one is the relative entropy. You could say, I want to move again in the direction of the gradient, but I don't want to get too far away now in relative entropy distance. So So this d of y given x is the relative entropy of two distributions. And this will give rise to a different update rule. Instead of moving a step in the direction of the gradient additively, we move a step in the direction of the gradient multiplicatively. So we multiply xt by e to the minus eta times the corresponding components of the gradient. And then we rescale it so we get a probability distribution. This is called multiplicative weights, or a multiplicative update rule. And that is what we're doing in this saddle point algorithm for zero-sum games. We have a strategy vector sort of implicitly defined over the whole set of strategies, and we're reweighting it exponentially according to the payoffs that we just learned from the other player. Now, there are a few more things you need to do to recover that algorithm. So what I've said so far is L1 norm mirror descent, but you also need to make it stochastic. So in stochastic gradient descent or stochastic mirror descent, instead of using the exact gradient, you use something random that equals it in expectation, but is often much, much simpler. Like you might look at only one data point, or a mini batch might be a handful of data points. And so that, it still follows the mirror descent logic, but it does so more efficiently. And the reason for L1 is that this allows sparse approximation. I guess also because we're working with probabilities that where naturally you're using the L1 norm. But in the zero-sum game algorithm, we have this distribution over all strategies, but we never write down the full distribution, right? We only work with a few samples from it. And for probability distributions, it often works to replace the description of the whole distribution by a smaller number of random samples. And why is this good? What's the point of all this? This can explain why we have that logarithmic dependence on the number of strategies, because our progress measure is going to be defined by whatever distance we use. If we use 2 norm distance, then the progress the 2 norm, when you relate it to the 1 norm, it's going to have these factors of square root of dimension, square root of n. Whereas the relative entropy is measured as an entropic quantity, and the entropy of a distribution can only be log n. And so kind of the amount of progress we need to make scales like log n instead of like square root of n, and that gives us more rapid conversions. Okay, so just to wrap up, as I mentioned before, I use Grover for completeness. Some people would say that square root speedup is not going to be ultimately enough for quantum computers to be competitive, given the overheads of fault tolerance and so on. I did Grover because it just felt like a missing hole in my knowledge of quantum algorithms, but put in an optimization algorithm of your choice and this would all work better. One place where it's particularly compelling is for Bayesian inference. When you're trying to sample from that distribution, you could use Grover to do rejection sampling and speed that up. But what you'd be doing then is quadratically speeding up a not very good classical algorithm, like brute force search or rejection sampling. But we know that with quantum walks, especially with sort of annealing style sequences of quantum walks, we're basically getting a square root speedup of one of the best known classical algorithms, right? Like Markov chain Monte Carlo is one of the best classical algorithms to sample from these distributions. So the fact that we can quadratically speed that up on a quantum computer is very promising. And finally, just a very general point about quantum algorithm design is that the classical computers are going nowhere, right? And they have their strengths. And so I think there's a lot more room for productively combining the strengths of both classical and quantum computers. And one example of this philosophy came when Garry Kasparov lost to Deep Blue. It was the first time that a computer had beaten the world leading chess master. And he helped popularize the notion of centaur chess or hybrid chess, where a computer and human play together as a team. And there was a period when those pairs had higher chess rating than the best computers, which in turn had a higher chess rating than the best humans. Unfortunately, it was a brief window, and now I think humans have less value added to computers during the play of the game. I guess we're still good at programming them. And that also illustrates the fragility of some of these partnerships, is that a problem has to be just the right size and difficulty so that both sides can meaningfully contribute to solving it. But in the case of classical and quantum computers, I think it's a very useful thing to keep looking at that. Okay, so I'll stop here. I hope you enjoyed the talk. I'll take any questions.
Thank you, Aram. That was an excellent talk. We get a big round of applause from me and everybody else who's listening live from around the world. So I'm gonna go to Slack and see if there are any questions. So there's one question from Peter who is asking if you see progress in QRAM developing over the next 10 years.
Yes, so I actually heard a nice talk by Liang Jiang from Chicago recently, who talked about this cool idea of, and he's not the only one doing this, in superconductors, you have a qubit, superconducting qubit, talking to many cavities. So for superconducting qubits, if you just do the easiest thing, you get a harmonic oscillator. And it's kind of hard to put in the nonlinearity, that's the Josephson junction. And it's hard and it lowers the lifetime. And one thing you could do is do that hard thing as rarely as possible. And so you have one qubit talking to many, basically harmonic oscillators, cavities. And those have very long lifetime. And so what you can do is you can stash something in there and then retrieve it later on. And you might even be able to use these as a sort of quantum RAM. And so that is a step towards quantum RAM that I think is interesting. But there's another issue with quantum RAM, which is these are so good, you could also probably make a universal quantum computer out of them. And so once you've built all the components of quantum RAM and it really works and it's scalable in terms of error performance, there's not like a general proof of this, but it seems like once you've done that, you're most of the way towards universal quantum computing. So I'm not aware of a technology where it's definitely going to make quantum RAM and it's not going to be useful for anything beyond that. It seems like this one, at least that I'm aware of, has also tremendous promise just for regular quantum computing as well.
Thanks. So there are no further questions in the Slack, so we still have a couple more minutes. So maybe while people start typing questions in the messages, maybe I can ask a couple of questions that I was curious about.
Thanks.
So you have this nice analogy between the stochastic L1 gradient descent and the saddle like algorithm. So I was wondering if one could go even sort of the other way around, like start from a different norm to build up a new algorithm.
Yeah, no, great question.
Using
because you see this sort of generality of mirror descent. You think I can plug in any norm, and I don't. The answer is it seems promising. I don't know how to do that. I think it's worth looking into. The one other thing that I'm aware of is for matrices, you could use instead of the ordinary relative entropy, you could use the quantum relative entropy. And then what you get is matrix multiplicative weights. So what you put here would be the matrix exponential of the sum of all the gradient terms that you've seen so far. And this is used for the quantum algorithms for semi-definite programming. They make use of this. And one thing that's kind of cute is if you look at these recent algorithms for quantum semi-definite programming, first of all, when they were proposed, we didn't even have any quantum algorithms for linear programming. So it's sort of like they did LP and SDP together for the first time. But also they all use an oracle data model. They assume you have superposition access. And when you try and get them to work for this data model, where you have classical data on one side versus models on the other, they no longer seem to work. So And so that's an example where you can generalize the mirror descent part to matrices, but the other parts, namely the sampling part, doesn't work so well. So for linear programming, the Y space, the thing you have superposition to, access to, those are basically the points in the primal space where you're trying to meet all the constraints. And it's enough just to sample from that distribution. Whereas if you try to make that semi-definite programming, then that turns into a density matrix. And you again have a bunch of constraints in the density matrix. And we don't know how to just measure the density matrix and get one sample that you can then pass over to the classical computer that can check to see if it satisfies all the constraints. Like in general, that doesn't seem like that would be possible. So trying to get that to work in the hybrid sense, I couldn't get it to work for reasons that were like it wasn't the mirror descent part that went wrong. It was the other parts related to the I guess you could say to the sparsification. Like for a probability distribution, I can represent it well by just taking a few samples, but for a quantum density matrix, it seems like I can't do that. But yeah, but your question I like a lot, and I would love it if anyone had more ideas of natural norms to look at.
Great, thanks. Going back to the Slack, Ross Duncan says, "Hi Aram, thanks for the talk. Do you have a feeling for what general characteristics a dataset algorithm should have to both, one, be feasible to load into a quantum computer and still have a quantum advantage in processing?"
That's a great question. Which Slack channel, by the way, should I look at?
So it's hashtag QuAlg 5.
Okay, thank you. So I guess the thing is, you have to, it has to be, so it has to be that the data access would be too painful for the quantum computer. So the data set is large enough for that. But also that just solving the problem is too painful for the classical computer, right? So once the classical computer has reduced the size of the data set, it could, it has a lot of resources, enough resources to access a big database, try to solve the model itself. So that should be a problem for the classical computer. And so basically, the way I would put it is there should be some aspect where the quantum computer does well. And so one thing I didn't talk about is quantum simulation, but I think that's another natural step to look at. And there should be but there should also be a large data set that makes that difficult. And so quantum simulation is actually fairly natural for n to the fourth if they're n orbitals. And just writing those down is too painful, and maybe a classical computer could certainly help compute those matrix elements, and maybe it could help reduce them. But I think the way I think about it is it should be difficult for both. The other thing where, and another way to think of the challenge is if you have a quantum algorithm where there's an outer loop where you're getting a speed up and an inner loop that still looks really painful. That's another place to look at this. So one thing that I'm looking at now are Ashley Montanaro and a few other people have some algorithms for branch and bound, which basically means the outer loop is a search over a decision tree where you get a very natural square root quantum speedup. And the inner loop is solving a linear program, but not the kind that we're here, but just sort of a general linear program where there might not be any quantum advantage. And it just is very sad to be doing an LP solver with all that arithmetic in quantum superposition. You're spending all this quantum resources for something that where there's no advantage. But you can't get around that because it's in the inner loop. And if the outer loop is doing the tree search, you can't pass off the inner loop to a classical computer. You have to run it in superposition. So that seems like an example where this sort of thing can be done, where you can say, well, maybe I can approximate the inner loop by something simpler and then use a classical computer to help with that. I haven't worked out exactly how to do it, but that's that seems like the type of place where data reduction makes sense, is where, or some sort of problem simplification makes sense, where the inner loop is something where you're spending a lot of time to no benefit, a lot of time just reproducing what a classical computer does.
Okay, excellent. Thank you, Aram. I think I don't see any more questions now, but maybe people will join in as the sun reaches this time zone. So thanks a lot for this wonderful